Section: Introduction. In this section, we introduce the context of our work. Transformers have proven to be a powerful and scalable architecture for sequence modeling, significantly advancing natural language processing. However, they struggle with long sequences due to the quadratic complexity of attention, which can be costly. Attempts to improve this inefficiency have encountered difficulties, especially in tasks that require long contexts, as removing tokens that might be needed later can make many token pruning methods ineffective. To tackle the inefficiency of standard attention, various strategies have been proposed. For instance, KV cache compression techniques like PALU use low-rank projections to reduce hidden dimensions, while Shadow KV employs low-rank key caching for long context inference. Other methods, such as Lin-Former and Performer, utilize low-rank approximations or kernel-based projections to lessen attention complexity. Sparse attention models like Big Bird adopt fixed attention patterns, but these can fall short in situations where static sparsity does not capture necessary interactions. On the other hand, state space models, SSMs, including architectures like Mamba, compress entire sequence histories into fixed-dimensional states, achieving linear complexity. However, SSMs struggle to represent long contexts with the same expressiveness as attention mechanisms. Stuffed Mamba points out the issue of state collapse, where RNN-based architectures like Mamba fail to generalize to longer sequences than those seen during training. Despite their efficient memory usage, the fixed-dimensional state of SSMs has a limit on how much information it can represent, and once this limit is exceeded, it cannot effectively retain earlier context. Our key insight is that we can leverage this limitation. SSMs can be adapted to learn how to compress groups of tokens into meaningful single-token states that maintain essential information. By training SSMs to perform variable-length token chunking, we can consolidate sequences into compact representations that the standard attention mechanism can then process, reducing the number of attention operations by the size of the chunks. In this paper, we present Attamba, a new architecture that merges SSMs with attention. Attamba uses SSMs for key-value projections, allowing for flexible chunked attention by compressing multiple tokens into a single state. This significantly cuts down on KV cache memory and attention computation costs by only caching the compressed chunk boundaries instead of all tokens. Our contributions include integrating SSMs into attention by replacing key-value projection matrices with SSM blocks, which allows us to compress multiple tokens into one representation while effectively attending to these representations, and introducing cyclic token chunking to reduce bias from fixed boundaries when compressing tokens into a single SSM state. We also demonstrate the feasibility of variable-length token chunking, achieving over 8 times savings in KV cache and attention with minimal trade-offs in perplexity. Next, we discuss related work. Transformers are essential for language modeling but face challenges due to the quadratic complexity of attention, which increases with the square of the sequence length, making computations both memory-intensive and costly. During autoregressive inference, the key-value cache size grows linearly with sequence length and embedding dimension, adding significant memory overhead. These issues limit efficiency and scalability, particularly for long context applications. To address this, methods like Lin-Former reduce complexity through low-rank factorization, while Big Bird employs sparse attention patterns to manage long sequences more effectively. Performer uses kernel-based approximations to achieve subquadratic complexity. However, these methods often struggle to maintain attention expressivity in long context tasks. State space models offer an efficient way to process long sequences. Mamba and its successor Mamba 2 achieve linear complexity by compressing sequence history into fixed-dimensional states, but they face challenges in retaining information over long contexts, as highlighted in Stuffed Mamba, which discusses state collapse. Hybrid models have emerged to combine the strengths of attention and SSMs. For example, Jamba interleaves transformer and Mamba layers, using a mixture of experts' approach to manage parameters and support long context modeling efficiently. Griffin integrates gated linear recurrences with local attention for better scaling and performance on extrapolation tasks. Similarly, Hawk uses recurrent blocks to outperform Mamba on various tasks. Techniques like multi-token prediction optimize efficiency by predicting multiple tokens at once, enhancing sample efficiency and speeding up inference. Our approach stands out by directly integrating SSM blocks within the attention mechanism rather than interleaving SSMs and transformer blocks. Section Summary. In this section, we discuss the limitations of traditional transformers in processing long sequences due to their quadratic attention complexity and explore various approaches, including state space models, SSMs, and hybrid architectures, that aim to improve efficiency. We introduce Attamba, a novel architecture that integrates SSMs with attention mechanisms to enable flexible token chunking, significantly reducing memory and computation costs while maintaining effective information representation. Section: Attention. In this section, we describe the attention mechanism we use. We start with an input matrix, where the number of rows represents the sequence length and the number of columns represents the model's embedding dimension. The embedding dimension can be broken down into the number of attention heads and the dimension for each head. We utilize projection matrices to compute the query, key, and value representations. The softmax operation helps us calculate the attention probabilities, which are the normalized weights. Next, we discuss state space models, SSMs, which maintain a hidden state that changes over time based on the input sequence and state transition matrices. The output sequence can be computed efficiently, with time complexity proportional to the product of the sequence length and the state dimension, and space complexity proportional to the state dimension. In our Mamba framework, we handle variable length sequences efficiently using cumulative unique sequence lengths, which allows us to index flattened batch sequences without the need for padding. We also cover the concepts of auto-regression and masking. Transformers are trained to predict the next word by modeling the probability of each token based on all previous tokens. To ensure that the model does not look ahead, we apply a causal mask during training. This mask prevents future tokens from being considered, allowing us to build up information cumulatively in hidden states. We introduce Attamba, which combines auto-regressive transformers and SSMs to compress information about prior tokens into a single representation for next word prediction. We can control which past information the transformers focus on using the attention mask. Attamba allows us to compress a set number of tokens into one using SSM blocks, maintaining linear complexity, and to use the attention mask to focus on these compressed states for efficient training and inference. In our formulation, we integrate SSMs into the attention mechanism to manage long sequences effectively. We replace the key and value projection matrices with SSM blocks, which process chunks of tokens and reduce computational complexity while keeping the context of the input sequence. We divide the input sequence into non-overlapping chunks and process each chunk auto-regressively. We ensure that we preserve all SSM outputs during training to account for incomplete chunks. During testing, we only need the final compressed representations of each chunk. By concatenating these, we can construct an appropriate attention mask. By using SSMs to compress chunks, we significantly lower the computational cost of the attention mechanism. We also find that SSMs can handle randomized chunk boundaries, which helps with complexity management. The size of the chunks plays a crucial role in how tokens are compressed. We define the chunk size as the number of consecutive tokens processed together, while leading tokens are those that retain full attention after processing. This resembles sliding window attention and maintains a constant cost. In our design considerations for Attamba, we validated several choices. We found that removing key value projection weights did not greatly affect model quality, simplifying the architecture. Using cyclic chunk boundaries across layers helped reduce bias from fixed boundaries. Increasing the state dimensions of SSMs showed diminishing returns, allowing us to minimize parameter overhead. We also ensured that leading tokens were not chunked to maintain attention on recent tokens, which improved model quality. Incorporating residual connections in SSMs further enhanced performance. Lastly, we confirmed that Attamba is robust to randomized chunk boundaries during both training and testing. Section Summary. In this section, we describe the integration of state space models, SSMs, into the attention mechanism of transformers to efficiently handle long sequences by compressing token representations and reducing computational complexity. We also discuss the importance of chunk sizes and leading tokens in maintaining model quality and the design choices that enhance performance, such as the removal of key value projections and the use of residual connections. Section: Experiments. In this section, we present our experimental results comparing the perplexity of the Wikitext2 test set. We trained on 10% of the DCLM baseline 1.0 dataset, using a batch size of 16 and a sequence length of 1024, with the MetaLingua framework. Our training involved approximately 1 billion tokens. We include the final Wikitext2 perplexity in the graph legend where relevant. Regarding transformer baselines, we note that Attamba reduces the sequence length for keys and values, which significantly decreases the size of the KV cache and the operational intensity of the attention map, especially during inference. Directly comparing Attamba with a transformer of similar parameters isn't ideal, as traditional transformers have much larger KV cache and attention map overhead. To create a fairer comparison, we constructed baselines with smaller KV cache sizes and attention map dimensions, as detailed in the appendix. Specifically, we reduced the attention model dimension to emulate smaller KV cache sizes and used sliding window attention during evaluation to create smaller attention maps. In our observations, transformers with 4 to 8 times larger KV cache and attention maps can outperform Attamba, but these comparisons do not account for equivalent memory or computational constraints. When we matched KV cache and attention map sizes, Attamba consistently outperformed transformer baselines, demonstrating its efficiency. Additionally, as the sequence length increases, transformers must proportionally reduce their attention dimension, leading to greater quality trade-offs. In contrast, Attamba shows strong and scalable token compression, with only a 2.2% increase in perplexity when moving from a parameter setting of 4 to 8, indicating its effective balance of efficiency and model quality, especially for long context tasks. We also conducted an extended training experiment with Attamba, Transformer, XMER, M in GRU, Hawk, and Mamba models, all within a parameter budget of around 60 to 64 million parameters. We trained for 100,000 steps over 8 billion tokens. We created appropriate baselines for transformers by reducing the model dimension in the attention mechanism to simulate KV cache compression and tested sliding window attention. Our findings show that Attamba outperforms fair transformer baselines and Mamba. While Mamba performs better for extremely long contexts, its model quality may decline. Attamba uses SSMs to compress fixed-sized token chunks, allowing it to attend to compressed token representations without needing to scale beyond the trained chunk length. The transformer with KV cache compression performs 5% worse but still generates an attention map, while the transformer with sliding window attention shows a notable decrease in perplexity due to a significantly limited attention map. Currently, our training is limited to 1 billion tokens on a 60 million parameter model using a single A6000 GPU. Our evaluation on Wikitext2 focuses on a highly local task, which is why our Attamba variant with a chunk size of 128 performs exceptionally well. This variant achieves a 128-fold reduction in KV cache size and attention operational intensity for longer contexts while maintaining full attention on the latest 128 tokens. This explains why it outperforms even Attamba with a chunk size of 4. Our analysis shows that the Attamba variant with a chunk size of 128 performs significantly worse than transformers, but Attamba with a chunk size of 8 and 64 uncompressed leading tokens offers substantial KV compression and reduced attention computation cost with a minor perplexity trade-off. However, a transformer with a reduced attention model dimension performs worse and does not save memory on the attention map. We recognize that our method does not improve the feed-forward network, as we keep the query sequence length to enable auto-regressive training of the transformer. Finding the right transformer design for fair comparisons is crucial to understanding the trade-offs of attention on compressed states. Adjusting the chunking strategy or training on more tokens may help address issues with high chunk sizes, but thorough evaluation on long context tasks and retrieval is essential to determine if effective attention can be achieved on compressed states. Lastly, all models reported were trained from scratch, and we plan to explore fine-tuning strategies and the robustness of models at chunk boundaries, as well as the impact of leading tokens in sliding window attention.